Thank you. It's a great privilege for me to make this presentation. And I acknowledge that our long-standing collaboration with Imperial, in fact, germinated when Howard was there at Imperial. And then we started off with a video conference, if you remember. And I greatly value your help in building this collaboration. So in this presentation, I would just give some broad overview of the water issues in India and specifically raise some concerns and science issues that we need to look at. When we talk about India, the first stress always comes from population. And these are real people. It's not a Photoshop image here. The population is growing continuously over the last about 4 to 5 decades. And we are very likely to overtake China. And I'm not saying that with any degree of pride. And as the population increases, the per capita water availability is coming down consistently. And we are already a water-stressed country in that sense. Bulk of our water resources come from the monsoon rainfall, which happens during the 4 months of monsoon, which is June, July, August, September. And majority of this water is used for irrigation purposes. As you can see here, about 75 to 80% of annual rainfall comes during those 4 months. And this poses a great challenge in managing the water resources at several different spatial scales. Now, when we are looking at the all India scenario, these are the major issues that we need to look at. For example, the first level stress comes from the decreasing per capita availability of water, extremely low efficiencies of water use, especially in irrigated agriculture. In fact, in one of the presentations that I made to the government officials, I used the figure of about 40%. I said it's extremely low, it's 40%. And then the government official said, if it is 40%, we would be extremely happy. It's about 19 to 20% is what they said. And then increasing frequencies of spatial extents of floods and droughts. You know, another important characteristic of our system is that the farmers are small in the sense that the land holdings are extremely small, about 1 acre, 2 acres, etc. And it is a question of livelihood for them and not an economic activity to produce food. And therefore, it is important for us to realize that the subsidies that are given to the farmers in terms of the free electricity and so forth, that translates itself into extensive use of, indiscriminate use of groundwater. And then we have rapid urbanization that has taken place over the last about 3 to 4 decades with very little scope for expansion of the infrastructure. We have interstate disputes of water. Several of the river basins face this. Lack of adequate quality and quantity of data. On top of all of these existing stresses, the climate change is most likely to be an additional stress, and we need to address all of these. So I'll just give a broad flavor of one of the projects that we are carrying out just now, along with C8 Wallingford and BGS of UK, and also the University of Dundee. We are leading the project from the Indian side. Essentially what we are looking at is that there are a large number of very small scale interventions that are taking place in the basin, and what are the impacts that these have on the larger basin scale hydrology. The smaller scale interventions are almost uncontrollable because individual farmers take these actions or the farmers associations take these actions. These actions can be in the form of check dams, bunds and so forth, and therefore while your models may be producing runoff, but we do not actually see the runoff on the small streamlet because the water is completely withheld by these farmers' bunds and so on. So we are addressing through this project the key scientific challenge of representing the many local small-scale water management interventions on larger scale. And this is a broad framework that we are using. Essentially what we are doing is we'll take well-instrumented agricultural catchment. This catchment has been studied for about 10 years. This is almost like a CZO. All parameters are monitored extensively and continuously. We also take urban catchments in the basin and then monitor these at a very small scale and at a very high time resolution. and then start looking at the impacts that these produce on the larger basin scale. That's a broad idea. And this is a watershed that I was talking about. This is an agricultural watershed which has been monitored over last about 10 years. And this is a small watershed, 84 square kilometers, completely instrumented. And we monitor all these hydrologic variables, including the soil moisture, the evapotranspiration, and so forth, the rainfall, runoff, and there is also a good geochemistry that is associated with this, and so on. Now, what we do is that we look at the point measurements as well as the spatial measurements of the soil moisture provided by the Cosmos sensors. The Cosmos sensors were donated to us by CEH Wallingford, and then start looking at our ability to simulate the soil moisture at small scales. Because if we want to measure, if we want to manage the water resources at those scales, we must necessarily have the soil moisture information at those scales. And we see that we are able to fairly well reproduce the soil moisture at those scales. And in fact, we have done it at 10-meter scale and 5-meter scale when we are using the Cosmos. 10-meter scale is the point measurement. And now there is also effort to start looking at the satellite measured soil moistures and so on. So this is how it looks. Essentially what this shows is that for the monsoon season and the non-monsoon season, how the partitioning takes place from the rainfall and what kind of soil moistures get simulated. One interesting feature that we find is that as we start averaging the soil moisture over a large region, the requirement of irrigation starts coming down. The requirement of irrigation to be put into the models, that starts coming down because the irrigations are episodic, and then perhaps at the smaller scales, the way they apply the irrigation, etc. So we were able to reproduce the soil moistures at those scales even without accounting for the irrigation when we are looking at the average soil moisture scenario. And this is the groundwater dynamics again at the rural scales or the agricultural scales. These are at different villages. Each of them shows different villages in the same 84 square kilometer catchment. Now what is interesting here is that as the groundwater starts depleting, these are all hard rock areas, and therefore these are the fractured aquifers. As the groundwater levels start depleting, there are, the levels start merging here, perhaps indicating that there may be a continuity in these fractures and aquifers and so on. But we are not absolutely sure yet, because this is just one data set that we are looking at. Now, similar to what we did on the agricultural catchment, we also start looking at the urban catchments. And we take the Bangalore city, and this central area here is completely supplied. It is supplied water through municipal supply, and we draw water from about 100 kilometers from the same river Kaveri, and then the distribution of water as well as the wastewater supply, that produces an enormous amount of leakage. In fact, the estimates are of the order of about 40%. 40% of the water goes as leakage. And whether this leakage in fact adds to the groundwater is another interesting question that we look at. And so this is a region that we are looking at. And what we conclude here is that the recharge that comes from the anthropogenic activities, mainly from the water supply as well as the wastewater supply, that far exceeds the natural recharge that takes place from rainfall and irrigation and so forth. And this is a water balance that we do. These are at 5 kilometers grid size within the city. And what these show is that the estimated recharge that comes from the pipes and wastewater supply, etc., this far exceeds the natural recharge at all of these grid points. These are at different grid points. Now, the questions that we are likely to address through this particular project is that the smaller scale interventions, typically these figures show the type of interventions that take place at really small scales. As I said, because the electricity is available free, the farmers put on the pump and then allow the flood irrigation to take place. In most of the cases, the water is applied far in excess of what is required. And then we need to look at the urban catchments like this. In the urban catchments, there is hardly any space for extra infrastructure to be created. Now, all of these have implications on larger scale basin hydrology, and then that's the thing that we're looking at. Typically, the science question that we're asking is, if we have monitored the smaller scales absolutely correctly, and we are able to parameterize it correctly at those scales, can we upscale it to the basin scale, if we have good signatures and good scaling up models and so on. So this is what we are looking at. Now, when we are talking about the water security issues, the floods, and specifically the urban floods that are recurring year after year in many cities in India as well as worldwide, these become important. And then we are looking at the changes in the IDF relationships, the intensity, duration, frequency relationships, as a response to the global climate events, whether the intensities are really changing at those scales as a response to global climate change. And the way we address this is that first we look at what has happened historically. Just look at the historical data. The temperatures in this particular city are known to be increasing. And similarly, we just look at the historical IDF relationships and see that at the time scales that are of interest in the urban areas, typically 1 hour and sub-hourly scales, the intensities have been, in fact, increasing at those time scales. Now, this just gives us a clue. Then we need to attribute whether it is, in fact, because of the climate change or urban heat island effect and several other issues. So what we then do is that we fall recourse to the CMIP-5 models and then bring it down in spatial scale, bring it down to the city scale. But much as they are good at large spatial scales, they are also good at large time scales. And therefore, on the time scale, we bring it down to smaller scales. Remember here that we do not actually reproduce the time series at those scales. What we are doing is we are producing the parameters of the extreme value distributions. For example, if you are looking at GeV, mu sigma k are the parameters. So we scale the mu sigma k, these parameters, from larger time scales to smaller time scales and convert that into the IDF relationships at those future time periods. What we observe is that the time scales of interest, like 15 minutes, 30 minutes, etc., these intensities are known to be increasing or are simulated to be increasing for future, whereas as the time progress, the time increases, for example, 24 hours, etc., there is hardly any uncertainty, and there is not much difference between the simulated and observed things. So we address the uncertainties associated with these using the Bayesian approach, and then provide a probabilistic IDF relationships. So that for use in designs, etc., we will be able to use. So that's the broad idea that I wanted to give. In conclusion then, if we want to look at the water security issues, the first requirement is to increase the irrigation efficiencies by using as much data, as much local data as possible, and therefore a good information on the soil moisture becomes important. And then because we are looking also at the floods and the climate change impacts, it is important for us to quantify the uncertainties associated with these impacts and reduce the uncertainties and also communicate the uncertainties to the policymakers. Thank you for your attention.
Thanks very much, Pradeep. Any questions?
Groundwater is lowering in different part of the rural landscape that you work on in India. I think it was in the very first slides. Yeah, so the next one. The next.
Okay, yeah.
Yeah, that's fine. So do you think it's something global in rural landscapes that groundwater is lowering? Because it has great implications for modelers and people who work on model development. So do you think this trend is global Yeah, this figure.
This one, okay.
Yeah, do you think this trend is global and we would expect it in the other part of the world in rural area?
Yeah, in fact, I have qualified it just in the previous slide that this was a drought period. 2016, 15, 14, there have been drought periods for us. And there was hardly any surface water available. Most of the irrigation came from groundwater extraction. And therefore, as you see, the last part, 2016, 17, etc., these have gone down significantly. But having said that, I think we should expect these similar trends elsewhere also because of the subsidies that are given to the farmers on electricity. And there is no groundwater law that exists in the country. And therefore, the farmers are free to use whatever amount of groundwater that they want. But on urban areas, there are different signals. You know, there are certain areas in Bangalore city itself where the water is groundwater is known to be increasing. So if you look at the basin scale, perhaps the agricultural lands will show a similar trend.
So at the basin scales, I didn't get your point. At the basin scale, it's lowering?
Yeah, at the basin scale, if you look at the agricultural areas, these trends may be expected in that particular Kaveri River basin. But on the urban areas, these signatures can be quite
Because
different.
of some stormwater management systems?
Exactly. The leakages that take place, for example, for the Bangalore city, we import the water from about 100 kilometers. And then all along the way, there may be leakages. And then the main leakages happen within the city when you are distributing the water. And that may add to the groundwater.
So how about in the other part of the world, in rural area, around the large cities in rural areas? So is it something that we have to expect?
I'm sorry, I did not get the question.
In other part of the world, so is it something that we have to expect to see lower groundwater level in future?
I think we need to make real studies on that. I may not
Because
be able to tell you.
it is great.
Okay, we're done. Do we have anyone else have any questions? Yes, sir.
Thank you. A quick one. Do you believe that we still need IDF curves? This is quite an old tool, and now with computers we have precise stochastic models, we have dynamic models that keep on improving. So do you really think that IDF is going to be useful in the future?
Thanks for the question. The IDF relationships we essentially used to get the design rainfall from to design the stormwater systems and so forth. Now, although we may have other means of getting these, classically the IDF relationships have been developed using the historical data, assuming the stationarity and so forth. So the question is whether the IDF relationships change in future. That means the design rainfall intensity for the same return period changes in future. Now that I suspect may not be available from the other methods.
Thanks very much, Pradeep.